Go.
Hi there, this is Team Shanghai Tower. Here are my group mates, Luke, Stephen, myself, and Rayson. Okay, excellent. So we'll begin with my introduction, and then I will pass on the presentation to Luke, who will explain to you guys about the methodology, then follow up with Stephen, who will explain about results, and finally, Rayson will conclude the day for our team. So, introduction. I will start with some basic information of Shanghai Tower, the motivation, why did we pick Shanghai Tower, and then I'll explain about the environment and design where Shanghai Tower is located in and how it looks like. Basic information. Shanghai Tower is located in the Lujiazui area in Shanghai, China. It is adjacent to two of the tallest skyscrapers in Shanghai, the Financial Center and Jingmao Tower. The building is designed by Gensler. Its above-ground height is 632 meters, it weighs 850,000 tons in total, and it has 575,000 square meters of built enclosed area. Our motivation for why we pick Shanghai Tower, of course, it is very evident that Shanghai Tower is located in Shanghai. It is the tallest building in China, and it is the second tallest building in the world. However, as we continue our research, we figure some more important implication with our research in Shanghai Tower. It is its meaning in terms of combating climate change, growing population urbanization, and sustainable development. Some explanation on the environment. Shanghai Tower is located in the subtropical monsoon climate, which means that for every summer, there will be several typhoons visiting these giant skyscrapers, making it really challenging for designers to design a tall building that suits this kind of climate. In addition to that condition, the soil condition is also really harsh, with Type 4 with China Building Code and Class F as IBC code. As you may tell from the picture on the bottom right, the site has soil susceptible to collapse during an earthquake, thus making it really challenging for tall buildings in Shanghai. However, as Shanghai buildings have stood in Shanghai since 2015, we can conclude that it has some excellent property in terms of its structure. The basic design of Shanghai Tower. Before I actually venturing into design, let me explain to you guys why it is important to build skyscrapers in urban area. Because of the process of urbanization, we now figure that vertical expansion is inevitable to accommodate the growing population. And Shanghai Tower is a great first step to combining the commercial center, offices, and recreational site into one. Now we can actually venture into the designing part. The aerodynamic property of Shanghai Tower is excellent with its twisting, tapering, round corner shape. This design also helped increase its sustainability by reducing the construction material by 40%. The Gensler's team, at the beginning of their project, declared that this will be an eco-friendly project. Therefore, they designed the Asia, which is something that will look like the picture on the top right. This is a buffer area between the exterior and interior area of the tower, help maintain the temperature and reduce the workloads for the air conditioning system. In addition to the above ground structure, its underground structure is also worth mentioning. It has 947 board piles with diameters ranging from 52 to 56 meters, help it to stand on the soil of Shanghai for so long. Okay. The planet we live on is currently facing and will continue to face climate change and population growth. We hope that by analyzing the natural frequency of Shanghai Tower through model analysis and harmonic response analysis, we can have a deeper understanding of the structure which holds so much excellent properties, and we hope that our findings will give some insights to the future design of the building. Now I'll pass on my presentation to the rest of my team. So Luke, you can go on. Let me stop sharing.
Thanks a lot for Shujing's great introduction about Shanghai Tower, and we all appreciate your hard work and thank you very much. Well, since I'm in charge of the modeling part of Shanghai Tower, so I'm gonna introduce the modeling and of the methodology of Shanghai Tower. Well, I divided this section into 4 parts, which are the source, difficulties and solutions, modeling, and limitations. Well, let's start with the source part. Well, at the beginning, we didn't decided like a clear target. So we did some research randomly, and it wasted us a lot of time, and we didn't find really a lot of useful information. But luckily, we got some like construction drawings from others' papers, like from the figure 1 to figure 3. The figure 1 is like an evolution of Shanghai Tower, which is from the simple interior structure to the complex exterior structure. And the figure 2, it is the base of Shanghai Tower, which is a cross section. And they're like, you can see that it could be some like accurate data, but actually they're not that accurate. And I'll talk about that later. And in figure 3, you can see that it is the division of Shanghai Tower, which it divided Shanghai Tower into 11 parts, which is unique from other divisions because other divisions are only 9 parts. And I choose this one because it's more like accurate and precise. Well, let's move on. Well, we went to the official website of Shanghai Tower, and we found those sponsors of Shanghai Tower. But unfortunately, we didn't didn't find any useful informations in most of them. But luckily, we got many useful informations from the Gensler website, and we found paradise in Gensler. Well, on the homepage of the Gensler website, we could see that there is a PDF which includes a lot of useful information, like the cross-section area with like really useful data, and also from this screenshot you can see that there are like really accurate area of each section of Shanghai Tower, and this helped us a lot in like building the model. And moving on, we faced a lot of difficulties during modeling, and we got some solutions here. Well, the first difficulty we met was like the sketch of the cross section cannot close. Well, you can see from the left sketch, you can see that I drew it just like it constructed me to do, and with those accurate data, but actually it's not that accurate, and they're like how to say that. However, it cannot close, and so in order to solve this problem, I used the function constraint, and I constrained the points with the lines, and so it became a sketch, like full sketch with closed one. But however, when we are like skinning it into a body, the software ANSYS Workbench kept reporting that there is an error. It says that like ultimate profiles are not allowed to skin. So it confused us a lot, and so we decided to like give it up, and we decided to simplify it to a Reliax triangle as the base of the Shanghai Tower. So you can see the figure on the right. Well, this is a Reliax triangle, and it has the arc length on the base of approximately 94.25 meters, and we like contracted to approximately 47.12 meters on the top of the tower, and that worked on really well. So it is a successful simplification. Well, the second difficulty we like met was the limitation of the scale of the limitation of the scale of the model. Well, the default was a limitation that whatever your sketch is, your sketch should not exceed 500 meters. I should give thanks to Curtis and Blair, because they told us that we could like turn on the large model support, and so in this way we could break through it, and we could have a 1-to-1 scale model with the height of 632 meters instead of like a 1/10 scaled model. And that made our model more accurate and also more precise. And this positively affected our future results. And this is like the evolution of our model. And also there's difficulty in these ones. Well, let's take a look at the figure 1. Well, this is the very first model we built. Well, it is super rough and super simple. Well, there are only 2 parts, and they're just like 2 triangular prism and with a twisting degree of 60 degrees. And we just wanted to have a brief look of the model to see what it will look like in the future. Well, in the figure 2, well, this is a more precise one, and we like divided into 11 parts, and the edges looks more smoothly, and it's more like the model of Shanghai Tower. But still, at that time, we didn't have the idea about how to like sketch or draw the notch. And but on the third draft, which is our final model, we found out how to sketch that V strike, which is the notch on the cross section, and that made us the final model, which is more accurate and precise. Well, unfortunately, there are lots of limitations and errors during our process of modeling. Well, you can see on the left side, we failed to do the control experiment due to the error in a telescope model. Well, the figure on the left, even though it looks like a huge cake, but we still want to call it a telescope model to make it seem more professional. And we could mesh it, but when we were doing that model analysis and the harmonic response analysis, the Workbench software always reports that there is an error. So it is a pity that we cannot continue that experiment, but hopefully we could figure that out and do it better in the future. Well, the figure on the right, it is the interior structure of Shanghai Tower. Well, it mainly contains like 12 posts and one core tube. Well, the core tube is like the square stuff in the middle. Well, it is extruded up, and there are 1, 2, 3, 4, 5, 6, 7, 8. Oh, there are 8 heel posts on where there are 2 on each side of the core tube, and there are also 4 corner posts. Well, it's pretty amazing that only these 12 posts and the core tube cooperate to like bear almost all the weight of Shanghai Tower, and that was super amazing. And here is a pity here, like we actually went to a field trip to Shanghai Tower to look for further data and further research, but it doesn't go like we imagined. So we went there and we want to meet the real estate, but by like communicating, they said that we need some license to get there, and so we didn't get any further data, and we even spent 180 RMB. That sucks. And this is it, all for our model part. And now let's welcome Stephen for our analysis part.
Okay, thanks, Luke, for his wonderful presentation. So let's continue. It's going out. Okay, let's continue. In this methodology part, I want to introduce some technical methods that we use to study this model. Generally speaking, we use model analysis as well as harmonic response analysis to study our model of the Shanghai Tower. For model analysis, it's a method to study the dynamic characteristic of a structure. And here, model is defined as an inherent vibration characteristic. For the harmonic response analysis, this is This is a method to investigate the stability of a dynamic characteristic of a structure. It can be used to study the steady state response of a linear structure against some harmonic changing loads at various frequencies, like some kind of wind, earthquake, or some other kind of force. Here is our technical roadmap. We combine these two methods to get the deformation diagram as well as the inherent vibration frequencies. This can help us to get the dangerous frequencies that need to be avoided because we know as these frequencies they can cause some kind of damage, like some kind of resonance. This is very dangerous to the structure. Okay, let's move on to next part. This is the result part. Firstly, I want to talk some data estimation because it's very hard for us to get the real value of the data. Well, maybe in the future we can consult the owner of the user of the Shanghai Tower to get some more accurate data. And I will also show some calculation results from the ANSYS workbench. Okay, it's the first estimation. Before for the first step, we have to make sure to use which materials in this model. To be honest, it's very easy to get the total weight of the structure, but it's very difficult to get the total volume because there are so many numbers, so many data on the internet, so many kind of them. Some kind of volume even take account of the parking area, which drove us crazy. So we use this. So we decided to calculate the total volume by ourselves. In this picture, I may find something. I believe this will work. Okay, in this picture, we add this 1 to 9 zone, and we put them together to get the total volume. And we use this formula rho equals to m over v to calculate the density of the material. And for the damping ratio, we use 0.8 to simulate the damper in the building. And for the wind load, we consult some paper or some official document and get an approximation external force that is about 4,776 kilonewton. Okay, and this is the results of our model analysis. We can see that the first 6 models are shown in the picture. We will discuss them later. And this is the result of the harmonic response analysis. The typical frequencies of the external loads and the amplitude of stress they cause are shown in the figure. And we can see in the picture that at some certain frequencies, the amplitude of the stress is much larger than some other frequencies. So we can get that at these frequencies, the structure can become unsteady and very dangerous. This is another kind of harmonic response analysis. The only difference is that here the amplitude is no longer the stress, but it is a kind of deformation. And it's the same case that at some certain frequencies, amplitude become much larger. Okay, and this is the results of the total deformation analysis. This is a small video. We can see that when we consider the damping, the maximum total deformation is much smaller than those cases without damping. We can see that the number is much smaller than this case. And we can see if there is no damping, the structure can cause some kind of torsional motion. You can see it's twisted. And here, the red part, there is a very, very large deformation, which can make this part maybe very dangerous. And it's the same case for the all 6 model analysis. They are all the same story. So you may ask, what can we get from these graphs? What does this imply? Maybe I should stop because if I continue my presentation, nothing is left for Wilson. So let's welcome Wilson to draw the conclusion of our research. Welcome.
Okay. A little bit nervous. Yeah, first time to give an English speech. Yeah, thanks to my lovely group members, and here it comes to our project's conclusion. Yeah. First of all, the results of our architectural model through model analysis are consistent with general architectural period requirements. As stated in the literature provided by the Professor Boca, we both know the frequency of super tall buildings is as low as about 0.05 Hertz, and it equals to about it's about 20 seconds period. And as you can see, this figure is a building structure without damping, and its period in the whose mic?
Whose microphone is on?
Hello? Who? Let's continue. Yeah. This figure is a building structure without damping, and its period in mode 1 is about 18 seconds. And that means the model we built has a certain reference value for the actual engineering applications. And so, and then we move on to the second conclusion. Following after Stevens' topic, after a harmonic response analysis of the model, we got two sets of data about the amplitude at each frequency, and you can see in there. Let's see the two sets of data both first, and we can find that several sets of frequency data are similar. For example, the frequencies of the model 1 and the model 6 in the harmonic response and analysis are similar to the frequencies in the model analysis. To be specific, just like the 0.048 is close to the 0.05566. And as a result, the structure resonates strongly under these frequencies. And we can see that there are larger deformations in the mode 1 and the mode 6. So we can prevent the structure from generating these kind of frequencies, and we can avoid the structure from being destroyed due to the resonance. And we originally planned to add a damper to the model, but we don't have time to figure out how to make it. So we just replaced the material of the whole building, and we set up the damping ratio as a 0.8. And these two figures show there can clearly see that after adding dampings, the structural deformations under the harmonic response analysis is significantly reduced. Although it seems like the value has not been decreased that much, but it has decreased for about 30%. It's a large proportion, right? So it can be seen that the damper is very helpful, useful to reduce the deformation of the building construction. Yeah. Of course, our project still have some limitations, just like we don't model the surrounding foundations yet, because the data of Shanghai Tower is very confidential. So we waste a lot of time at the beginning, and so we don't have time to model the surrounding foundations. But I have checked the depth of the 9 layers and 10 sub-layers, and also I know all the average soil weights of them. So maybe we can finish later. And and I roughly calculated the magnitude of the wind load on the model, because the surface of the surface area of the model cannot be determined. It's curved. So I approximated the surface to a plane, and I assumed that all the forces on the windward surface are all pressures. So I don't need to plus any numbers. And then I ignore the characteristics that the wind load carrier type coefficient changes with height. So I finally got an approximation of the wind load, and put it in the force. Yes, it's too imprecise, and yeah, we haven't done the seismic response analysis yet. And me and my group members are all looking forward to the further research in the future if we have time. That's our reference, most from Tongji University. Yeah. Let's welcome Luke to introduce our contribution to the project. And we all know Luke has a nice voice.
Okay. Well, our group members did a really great job, and I appreciate all their hard working. And this is our contribution for respectively. Well, the first one is me. Well, I mainly focused on modeling Shanghai Tower and writing the methodology, the modeling part in both the paper and the report, and also like doing the manual calculation and communicating with concerned personnel. And as for Stephen, well, he chooses the topic and coordinated the group work and mainly focused on the technical analysis part of the research. Well, for Xu Jing, well, she did some literature research, organizing report and presentation, learning general knowledge, and maintaining source cited. Well, as for Rusin, he checked literatures, helped determine the topic, do calculations with professional knowledge. Well, before we end our presentation, we would like to give our thanks to the professor, the TAs, and our classmates. Well, first we'll thank the professor for the all the theoretical knowledge and all the supports and the suggestions on how to on modeling and analysis. We'll also give thanks to the TAs, Curtis and Blair, for their kind helping and their friendliness, and they're not only our teachers but also our friends. And also we give thanks to all our classmates, and thank you for your companion, and hope you guys have enjoyed. And thank you very much. Thank you.
Excellent. Excellent presentation. I learned a lot. I wonder if you had read anything about the foundation of the tower. Do you know what kind of support system the tower has? Did you read anything about it? I think it's like the Khalifa Tower. It's supported on piles.
I'm sorry, sir. We didn't have our earpods, so we didn't hear a question.
Okay.
Could you repeat, please? Thank you.
The question is, have you read anything about the foundation support for the Tower of Shanghai?
Foundation support?
How is it supported?
Well, that's the profession of Reason. Maybe Reason could answer that question. Reason needs some.
Can you hear me?
Yeah.
Okay. Yeah, sorry, I can't find my AirPods. Yeah.